Hello student, welcome to our physics discussion, that is physics in a smart way. For some time, I have been involved with uploading some videos, preparing some videos on, on mathematics, that is for class 11 students who have just promoted themselves from class 10 to class 11. So those videos were on mathematics, which is useful to physics. Applied mathematics, you may say. So far as class 11's curriculum is concerned, our last videos were of Newton's law, and Newton's law, that is particle dynamics 1, is a vast one. There are many aspects to it. I think, as I remember, my last video was on friction. We again go back to that. We consider another aspect of Newton's laws, NLM, that is your momentum and its conservation. So far as momentum is concerned and its conservation is there, we got a rule which is a very, very powerful rule, and that is considered as one of the pillars of the physics, along with some other principles like energy conservation and all, and that is known as principle of the conservation. You must excuse my bad handwriting, of linear momentum. Linear momentum. We must stress upon the word linear because momentum has got a cousin in rotation that is known as angular momentum. That has got its own conservation rule also, and that's a very powerful. So principle of linear momentum conservation is considered as one of the fundamental principles, and as I told you, is also considered as a pillar of physics. If those pillars collapse, then entire physics will be collapsing. But to comprehend, to know it is very easy. That very simply says, if on a system there is no force which is external, or if no, so to say, external force acts, or if some external force act but their resultant is zero. So basically that says sum of the resultant of all external force is zero. The momentum of the system remains constant. If external force acting on a system, if there is a single force, then that force doesn't act. If there is a single force, then no force acts. If there are many forces acting on the body, we can also create that condition. And if by chance the resultant of all the forces come to a naught or zero, then also that is the same thing as if no force is acting. So momentum of the system, we know symbol of the momentum is P, and P is a vector quantity. So momentum of the system remains constant. So basically, we write the entire statement in one line. The momentum of a system remains conserved or remains constant if no net external force acts. That's about the principle of momentum conservation, writing it. But thing is that the principle may look good, may look very fine, may look very simple on paper, but to use that in practice or in solving our problems, that requires a bit of insight. And if by chance somebody is not able to use it, then that shows a thing that knowing a thing and realizing it are two different issues altogether. You may know a thing, but if you have not realized that, then you cannot apply that. And that most often happens in the case of physics for students, because a student A student uh, may be knowing a thing, but he or she doesn't understand that whether our understanding is complete or not. That very simply I say, we do not know what we do not know. But the people who set questions for us, they do know what we do not know. So thereby we face problems. Okay. Okay, let us come back. Otherwise, that will be a very lengthy speech. So principle of linear momentum conservation, on the basis of that, I am considering a question. We pick up a question and the question is there on your screen. But as I told you earlier beforehand, once you get a question, do not jump to the solution because I'll be continuing to discuss the solution. So pause the video or stop the video there. Think about that, do something on your own. And if not done, or if you want further clarity, you may go for the solution also. If you are able to solve it, then that is well and good. Still then, I will advise you to go for the solution because sometimes we may be solving it, but that may be a coincidence. That may not be technically very much correct. Okay, so to avoid all those issues, you have to go through the whole thing. But first of all, don't go to a state where every time you require spoon feeding, that won't work in case of so far as understanding of the physics is concerned. So we go for the question that is there. A person of mass 50 kg, there is a person of mass 50 kg is on a trolley of mass 100 kg. The trolley or flat car is of mass 100 kg and the trolley is moving with a constant velocity of 10 meters per second on a smooth horizontal surface. Using the words like smooth horizontal track, it is there deliberately to avoid friction and all those. So friction doesn't come in here and create further complication. We do not want that. Okay. And then the question continues, what will be the change in the velocity of the trolley? Change in the velocity of the trolley if the person runs backward. We have taken the trolley motion towards right. That is the forward direction. Now the person walks or runs backward with a constant velocity of 6 meters per second on the trolley. The words may be, the question if I am to change the words, if I am at the liberty of changing the words, then I can say 6 meters per second on the trolley. I can say 6 meters per second with respect to the trolley, taking the trolley as the ground. On that ground, he is running with a speed of 6 meters per second. Okay. So thereby, if he runs like that, initially he was not running, then what will be the change in the speed of the trolley as the question asks us. So if I am to go into the solution, but as I told you, you must give a pause to the video, think about the situation, go for the question once again, try to understand what it really asks and how we can be able to use the so-called momentum conservation here as we have hinted at it. Okay, so far as the solution is there, we try to avoid the newest principle that we have learned, that is momentum conservation. We try to think of the situation using our old Newton's law style. Of course, momentum conservation is also another way to express the so-called Newton's law. But you know, when we did first learn Newton's law, that was not in the way of momentum or its conservation or something else. that was concerning our acceleration, change of velocity, something like that. All those things, and you know better, I shall not waste time on it. So at first, we try to avoid the momentum conservation using our early ideas on Newton's law. We try to find out when the person starts to run or starts to walk like this towards left, whether the speed of the trolley will be changing or not. Because some of you may be having some doubt. Okay, you may be saying, your mind may be saying, okay, he's walking on the trolley, he's not walking on the ground. So why the speed of the trolley will change? We are trying to ascertain that. Let us say, we consider the trolley. So far as the trolley is there, we consider the trolley. So far as the trolley is there, we know the person is walking. When the person is walking or running, we know the mechanism of taking a step whenever we walk or we run. When you take a step, your front leg is up and back leg presses the ground like this. Whenever you take a step, the front leg is up, that has lost all the contact with the ground, but with the back leg, we press the ground like this. Okay, so because he's pressing the ground in this fashion, when he's walking towards left, he exerts a force in this direction. And that inclined force has got a horizontal component. And that horizontal component is to increase the speed of the car. Of course, difficulty is there when he takes steps, applies force, and the force has got a horizontal component. The force that he applies or his horizontal component is not of a constant value. The force is discrete. It is not continuous. Mind my words. The force comes only when he takes a step. So that is not a regular force. It's a very difficult force if somebody is speaking mathematically. But whatever it is, because his force, the force that he applies on the trolley, will be having a horizontal component that is towards right, and that horizontal component is to cause acceleration and change the velocity of the car in a positive way, trolley in a positive way. That means velocity of the trolley will be increasing. I think we are convinced now. We are convinced now. So if you try to solve it, if you try to explain the situation, why due to his work the speed of the car will change, we have explained it using our own Newton's law. But some of us may not like it. They may claim, okay, now we are in momentum and its conservation. Let us try to see the situation with the lens that is momentum and its conservation, or using the momentum and conservation wedge. So I am removing the thing that we had explained here. We need some clear space. If somebody takes momentum and its conservation, then the first question will be about the system. The thing is, what is our system? We know momentum of a system is conserved only when external force is zero. External force is zero. We know when he is walking, he is exerting a force on the trolley, the person is exerting a force on the trolley. Trolley is bound to give equal and opposite reaction. If you consider all those things, then we'll be entangled in that. Rather than if I consider person on the trolley as the parts of a single system, then you know these forces, they become internal forces. And as Newton strictly says, we do not have to involve with internal forces, only external force do matter. So we got here maybe we can say at present, maybe we can avoid those forces that when he is running, the force that he is exerting on the trolley and the counter reaction that the trolley gives to him, we can avoid all those things. If you take the trolley and the person as a single system, then those forces he exerts on the trolley, trolley gives to him the reaction, they become internal forces. So with a view or with an inclination like that, so we consider our system that is person plus trolley taken together. But some of us might object. Their objection can come like this. They may say, how it is true, some external forces do act on the person and trolley. At least they have their self-weight and all those things. Ground will be giving reaction. But fortunately, we can save ourselves because we know we are interested in the motion. And when we say motion, the motion in the horizontal direction, yes, external forces like gravity force and the ground reaction do act on the person and the trolley, especially the trolley, but those are vertical forces, and vertical forces are not to influence the horizontal situation or the horizontal happenings. So thereby we ignore them horizontally because we have mentioned or the question mentioned that yes, a force had got a chance to come in and that force would have been horizontal. That is the force of friction. But the question avoids those friction force by mentioning the word smooth horizontal track. So we neglect the vertical forces because we are mostly interested in the horizontal momentum of the things. So if that is so, we now understand that there is no horizontal force acting on the person and the trolley system from outside. From outside. So if there is no net external force, specifically horizontal force, acting on the person and trolley system, momentum, horizontal momentum of the system will be remaining conserved. So if you consider two cases or two states, state one, when the person didn't start to work, state two, he is now working. When the person didn't start he has not started to work. So then the system, he was standing at rest on the trolley, was having a mass of 150 kg. That too, velocity was towards right, mind it, momentum is a vector quantity. So velocity I can write as 10 I cap. So that is 1500 I cap. Okay, kg meter per second towards right. That was the initial momentum when he has not started to work. Now he is working. We know because initial momentum was 1500 towards right and no net external force acts. So momentum will be always maintaining itself at that value. But when he is working towards left, we know deliberately he is creating a negative momentum or towards left momentum. But momentum is to be kept sacred or kept constant. So now the trolley will be forced to increase the speed from 10 to something higher so that some additional momentum will be created which will be counterbalance the person's negative momentum that he is creating by virtue of its working towards left and keep the entire momentum, get the entire momentum back to the initial level that is 1500 towards right. Am I clear? If you are not clear, then you can run the video backwards or maybe we can talk it out. Initially, when he has not started to work, our momentum was 1500 towards right because he's at rest on the trolley. Total mass is 150 and the velocity was 10 I cap. We may say plus 10 or somebody can say 10 I cap, both are true. But now when, so because initial momentum is 1500 towards right, 1500 towards right, and no net external force acts, so momentum will be always conserved, always maintained constant at 1500 towards right. But when he starts to walk towards left, he deliberately tries to spoil it by creating a negative momentum. So now what does trolley will do? Trolley will be increasing its speed, or the speed of the trolley will be increased. Some additional positive momentum will be created, which will be offsetting, counterbalancing the negative momentum of the person and get the whole momentum back to the initial value, which was 1500 towards right. Okay. Now, our job is to represent mathematically or by numbers. Partly we have said so, partly we have done so, the thing that we have just discussed. So thereby using momentum idea, also you know the speed of the trolley will be increasing. Let us say the speed of the trolley or the increment is delta V, because the question asks us how much is the change in the velocity. The change is delta V. Okay, so now we claim that when the person is walking, the trolley speed has changed from 10 to 10 plus delta V. In plus of delta V, you could have taken X or Y or whatever it is. I am taking delta V. Okay, so if you express it, momentum conservation is a very, very powerful idea. Usually that doesn't take more than 1 or 2 steps to find the answer. But the thing is that how we are able to write it, or whether we are able to write it correctly or not. So we say horizontal momentum, that is P initial, will be equal to P final. Okay, and now we put in the quantities. Initial momentum, when you try to write it, immediately a question comes in, is that we is writing this equation, we immediately we are writing. Then the question can be, who are you? Only an observer. An equation can be written by an observer or a reference frame. Where he is? Where is the observer? What is the reference frame? We have to make it clear. So it is the problem now. So we assume that the entire thing is observed and written by an observer who is standing at rest on the ground. If you put the observer on the trolley, then he is moving, and a moving observer sees all the things in relative that might cause complication for us. So always we try to find out, we try to write the equation from the point of view of a reference frame or an observer who is standing at rest on the ground, and inertial observer. So this observer sees that the trolley is having a mass of 100. Initial momentum I am writing. The person having a mass 50 and their velocity was 10 I cap, and mind it, momentum is vector quantity, has to be written strictly, will be equal to final. Now the thing is, what is the final state? Already we have described. The final state is when he is walking. You should not take final state as when he will be stopping. So when he stops, again the whole thing will be coming back to initial level. So he is walking, he is continuing to walk, is our final state. In the final state, it will be slightly difficult to combine them together and write the whole momentum in one go. Let us make them separate and then add it up. Trolley, which is having a mass of 100, now has a velocity not 10, but 10 plus delta V. I cap. Okay, trolley momentum is complete. And plus or minus person's momentum. Person is having a mass 50. And what is the velocity? You may be inclined to write 6 or minus 6. No, it's not true. Person's momentum as seen by, from this reference frame, as seen by the observer who is writing all those things. The observer sees that the person, I am writing this person, the person is on the trolley, and because trolley is going towards right with a velocity of 10 plus delta v, so the person automatically acquires that speed. You put, when the trolley is moving, you put a bag full of potatoes on the trolley, anybody on the trolley is bound to have the trolley speed. So because the person is on the trolley, it will be automatically inheriting the trolley speed, that is 10 plus delta v towards right. And on the trolley, he's, with respect to trolley, he's having a speed of 6 towards left. So when we write the person momentum, we say plus person mass is 50 because he is on the trolley. So he is having the trolley speed, that is 10 plus delta v I cap, and he is having his own speed, velocity, that is 6 I cap towards left. So minus 6 I cap. I think my statement is clear. That is only one line. We write everything. And because in the entire expression, we got one unknown, you solve it yourself. I won't be helping you because you don't require my help. So delta V comes out as 2 meter per second. Find it yourself, open up the bracket, cancel the similar terms, delta V will be automatically coming out, simple algebra, and that comes out as 2 meter per second. So the trolley speed will be increasing as the question asks, increasing by 2 meter per second, or one may say from initial velocity of 10, now the trolley moves when the person, or during the time he'll be continuing to walk, the trolley will be moving with a speed of 10 plus 2, that is 12 meter per second. Okay, that's all for today. In my next videos, we shall be going to other topics. So thank you for your viewing.